there! It's me again, your teacher Shane. And today, we have a new lesson for this video. So, good day everyone! Welcome to our new lesson for today. I hope you're having a wonderful day and you learned something and exciting. Please take a moment to relax, focus, and prepare your mind for this lesson. Before we begin, first let us have a few simple rules to help us learn effectively, even while watching this lesson. First, listen carefully. Yes, we have to listen carefully to this lesson. And second, avoid distraction. Put away your phone or the gadgets not used for studying. And third, take notes. Yes, we need to take notes while watching this video. And lastly, participate mentally. Pause the video if you need to think or answer the guide questions. So, let me start a simple questions. Have you noticed that when you pump a bicycle tire, the pump becomes warm? Or when you touch your phone while it's charging, it feels hot. Where does the heat come from? Oh, so these are examples of energy changing forms. In science, we explain this everyday experience using thermodynamics. This thermodynamics is the study of heat, energy, and work. So, based on the examples and questions, what do you think our lesson for today? Class, what do you think? Yes! Very good. It's all about science for heat and work in thermodynamics. And second, work done during volume changes. This too is the types of first law of thermodynamics. Before we begin our lesson for today, let's have first our learning objectives. After watching this lesson, you should be able to explain the science of heat and work and describe how work is done during volume changes, and appreciate the importance of thermodynamics in understanding real-life situations involving energy use. And lastly, apply your knowledge by solving simple problems related to heat and work and volume changes. Now that we know our focus for today, let's begin learning about how energy is transferred as heat and work in thermodynamics. But first, let us know what is the first law in thermodynamics. Here's a video that I will tell you about the first law in thermodynamics that I just found out through my research.
Or what is the first law of thermodynamics? The first law of thermodynamics is also known as the law of conservation of energy. Essentially, it states that energy cannot be created or destroyed, only transferred or transformed from one form to another. This law forms the foundation of thermodynamics, which is the branch of physics that studies the relationship between heat, energy, and work. In simpler terms, the first law tells us that we can never get something for nothing. All the energy we use comes from somewhere. How does the first law of thermodynamics work? Now, let's say we have a system. Let's say it's a gas in a container. The first law tells us that the change in internal energy of the system is equal to the heat added to the system plus the work done on the system. This is commonly written as delta U is equal to Q minus W, where delta U is change in internal energy, Q is the heat added, and W is the work done by the system. In other words, the change in the energy of the system is equal to the energy that puts in minus the energy that taken out. Let's talk about the real life application of the first law. So how does all of this apply in real life? Well, one of the most obvious example is in heat engines. Heat engines are devices that use heat to do work, such as a car engine or a power plant. The first law tells us that the energy input in the form of heat must equal to the energy output, which is in the form of work. This is why cars and power plants are designed to be as efficient as possible. Any wasted energy means less work has been done. Another example is in home heating and cooling. The first law tells us that when we heat a room or cool it down, we are not actually creating energy. Instead, we are simply transferring energy from one place to another place. This is why it's important to have a well-insulated home, as it helps to prevent the transfer of energy from the inside to the outside and vice versa. By using energy efficient heating and cooling system, we can also reduce the amount of energy needed to maintain a comfortable temperature in our homes. Understanding the law of thermodynamics can help us make informed decisions about how we use energy and how we can reduce our impact on the environment.
Based on the video that I will present to you, the first law of thermodynamics states that energy cannot be created or destroyed, only transferred or changed from one form to another. For example, when you heat a gas inside a piston, the gas energy increases. Part of the heat raises the temperature of the gas, which is the internal energy, and part of it pushes the piston upward, which is work. The energy you put in is never lost. It is just shared between heat and work. So in simple terms, the first law in thermodynamics, it just cannot be created or destroyed, only transferred or changed from one form to another. Now that we understand the first law in thermodynamics, let's delve into our lesson for today. First, what is the science for heat and work in thermodynamics? Let's define it. We describe the energy relationships in any thermodynamics process in terms of the quantity of heat Q added to the system and the work W done by the system. Both Q and W may be positive, negative, or zero. In this figure 19.3, a positive value of Q represents heat flow into the system, with a corresponding input of energy to it. Negative Q represents heat flow out of the system. A positive value of W represents work done by the system against its surroundings, such as work done by an expanding gas, and hence corresponds to energy leaving the system. Negative W, such as work done during compression of a gas in which work is done on the gas by its surroundings. Represents energy entering the system. We'll use these conventions consistently in the examples in this chapter and the next. And now, I have something to show you with an example of what is the signs for heat and work in thermodynamics really are.
Track energy changes, scientists use specific sign conventions for both heat and work, where positive and negative signs clearly indicate the direction of energy transfer relative to the system we are studying. This standardized approach is absolutely vital for the first law of thermodynamics. This fundamental law states that energy cannot be created or destroyed, only transferred or changed from one form to another. By using clear sign conventions, we ensure that energy conservation calculations remains consistent and universally applicable, no matter where or by whom the analysis is performed. Without these agreed-upon signs, communicating and understanding complex thermodynamic processes would be nearly impossible. Now let us break down how these signs are assigned. First, we must clearly define our system, which is the specific part of the universe we are focusing on, and its surroundings, everything else. For heat, symbolized as Q, the rule is straightforward. If heat energy enters the system from the surroundings, it is assigned a positive value. Think of a pot of water on a stove absorbing heat to boil, that is positive heat. Conversely, if heat energy leaves the system and goes into the surroundings, it is assigned a negative value. A cooling cup of coffee releasing heat into the room is an example of negative heat. For work symbolized as W, the convention refers to mechanical work, often involving volume changes. If work is done asterisk on the system by the surroundings, it is assigned a positive value. Imagine pushing down on a piston to compress a gas within a cylinder. You are doing work on the gas, so it is positive work. On the other hand, if work is done asterisk by the system on the surroundings, it is assigned a negative value. If that compressed gas then expands and pushes the piston outwards, the system is doing work asterisk on the surroundings, resulting in negative work. This careful application of positive and negative signs allows the simple yet powerful equation for the first law of thermodynamics, delta U equals Q plus W, to hold true across all scenarios. Here, delta U represents the change in the system's internal energy. Whether you are analyzing the energy transformations in a living cell, a power plant, or even a star, these conventions provide an unambiguous way to account for every joule of energy. Mastering these sign conventions for heat and work is more than just memorizing rules. It is about developing a fundamental understanding of how energy interacts within and around a system. This insight empowers you to accurately analyze and predict the intricate energy flows in any physical or chemical process, making sense of the dynamic world around us.
So, do you understand what being said in video? Yes. So, thermodynamic signs are like a bank account. When energy is deposited into the system, which is heat in, or nisulod ang kainit, it's called positive Q, which is Q is represent quantity of heat. When money goes out, which is heat loss, so ang kainit na pod nawala. It's called negative Q, which is quantity of heat. When the system pays other by doing work, it's positive work. And when others pay the system by compressing, it's negative work. So, do you get what is the meaning of signs for heat and work in thermodynamics? Yes. So, with these conventions, we can correctly apply the first law of thermodynamics and understand how energy flows during physical processes. So, nahibalaan naman ninyo kung unsa ang science for heat and work in dynamics. So, let's move on into another type. Now that we understand the science of heat and work using our analogies, let's continue with the next part of our lesson, which is called work done during volume changes. In the given picture below, a simple thermodynamic system is a gas trapped inside a cylinder with a movable piston, similar to what is found in a car engines, steam engines, refrigerators, and air conditioners. When the gas is heated, it expands and pushes the piston, doing work. When it is compressed, work is done on the gas. We can understand this system is two ways: microscopically, by looking at the motion and energy of individual gas molecules, and macroscopically, by using measurable quantities such as pressure, volume, and temperature. Even without studying molecules directly, the basic law of thermodynamics still work, showing that energy is always conserved and transferred as heat or work. In figure 19.5 shows a system whose volume can change a gas, a liquid, or solid in a cylinder with a movable piston. Suppose that the cylinder has cross-sectional area E and that the pressure exerted by the system at the piston phase is P. The total force F exerted by the system on the piston is F equals P and E, where F is total force and P is the pressure and A is the area. When the piston moves out an infinitesimal distance, dx, the work dw done by this force. But where dv is the infinitesimal change of volume the system. Thus, we can express the work done by the system in this infinitesimal volume change as dw equals p dw. In a finite change of volume from V1 to V2, we can derive this formula, which is W equals L to the power of V2 and P dV over the V1. W represent work done in a volume change, and V2 represent upper limit or final volume. P dV represent integral of the pressure with respect to volume. V1 represent lower limit or initial volume. In general, the pressure of the system may vary during the volume change. For example, this is the case in the cylinders of an automobile engine as the pistons move back and forth. To evaluate the integral in equation 19.2, we have to know how the pressures varies as function of volume. We can represent this relationship as graph of P as a function of V. PV diagram described at the end of section 18.1. In figure 19.6 shows a simple example. In this figure, equation 19.2 is represented graphically as the area under the curve of P versus V between the limits V1 and V2. In this section 6.3, we use a similar interpretation of the work done by a force, which is F, as the area under the curve of which is F, versus X between the limits x1 and x2. According to the rule we stated in section 19.1, work is positive when a system expands. In an expansion from state 1 to state 2, in figure 19.6, the area under the
Hello, this is our next video in a series of videos going through Young and Friedman's University Physics. And the sections in Chapter 19 is on the first law of thermodynamics. Most of the sections are pretty small, but I've decided rather than trying to join them together, probably it's best to just have shorter videos, which of course I'm wasting time with this preface. Section 19.2 is about work done during volume changes. In other words, if there is a heat situation such that the volume of something expands, maybe I have a balloon with some air in it, and somehow the room temperature goes up and the volume of the gas in the balloon expands. So there's work done, positive work done, as this happens. And so there's work done during a volume change. So again, I apologize for my hand-drawn ditty here, but I don't want to intrude on the copyright of real artists. But anyway, you get what you pay for, right? All you have to get for this video is watch an ad. Anyway, so this basically the force that is done by pressure on a particular area. Let's say we have a cylinder, and let's say that this thing at the end is movable. Let's say it, as the pressure is on this, it moves, to the right. And so the force exerted here is the pressure times the area. Now that makes perfect sense, but I did try to think, okay, how can I be certain of this? Well, you see, pressure, by definition, is the force per area. So P equals F over A. So all we have to do is multiply both sides by A, and we have that the force is the pressure times the area. Ta-da! So it makes perfect sense. So force equals pressure times area. Now we know that work is force through a distance, right? Force through a distance. So if we take the kind of derivative of both sides, the incremental change in work equals the force, assuming it's constant here. Well, hold that thought. Through a incremental distance, okay? If work equals force times a distance, then the incremental change in work is the force times the incremental change in distance. But we've just seen that force equals pressure times area. So we can substitute PA for F. And now we have that the incremental change of work equals the pressure, assuming, well, I'll leave it at that, pressure on an area through an incremental distance. Okay, now we know that the area, which is two-dimensional, times a incremental change in depth is the volume, right? Area is two-dimensional, volume is three-dimensional. So if we take the area of something and multiply it by an incremental change in the distance it moves, we get the incremental change in the volume. And so what you can see where this is going, right? Area times dx, we can substitute dv there, and we have that the incremental change in work equals the pressure times the incremental change in volume. Now we're getting somewhere. So now if I want to know then what the work is, I just integrate both sides. And so the integral of dW is W, work, the amount of work done. So it's the integral from V1 to V2 of the pressure times the incremental change in volume, okay? All right. Now, if the pressure is constant, then a constant comes out of an integral, right? The P comes out. And then we just have V2 minus V1 because the pressure has been constant. So if the pressure is constant, then the work equals the pressure times the ending volume minus the beginning volume. Okay, so here are some helpful little ditties by Jack and Diane, or by Young and little ditty by Young and Friedman. And so we can use these to solve some problems. Okay, again, I apologize for my hand-drawn diagrams, but hey, this is free. So let's say that the pressure goes down and the volume increases. Okay, so we've got a pressure going from a higher to a lower, P1 to P2. Okay, it's going from up here to down here, and we have a volume that is expanding, because it makes sense. If the pressure decreases, then the volume is going to, because PV are inversely related. So the integral from V1 to V2, the integral is simply the area under this curve, right? And so the integral is the area of this space from V1 to V2 of P, pressure, dV. And it's going to be greater than 0, right? Because the volume is expanding, and so the work is positive. Okay, now what if it goes the opposite direction? And they use, Young and Friedman tell us that they're going to use this hash mark to show us that it's negative. So here we have an increase of pressure from here to here. So we have an increase of pressure. The pressure goes up, and because the pressure goes up, the volume goes down. They're inversely proportional, right? So here, it's the same thing, right? The volume from V1 to V2, PdV, that's the same quantity. But here it's going to be negative, right? Because negative work is happening in that particular situation. And Young and Friedman are careful to warn us to make sure that so like I put V2 and V1, be careful which is first and which is second. This is a difficult concept. The starting one is 1, and the finishing one is 2. Mind blown. Okay, now if the pressure is constant, so let's say the pressure stays the same. I didn't even put a hash mark here, but let's say the pressure stays the same and the volume increases. Then there's still work done, but it is simply the area under the curve here. So it's going to be, the area of a rectangle is the length times the height, right? So the pressure, oops, sorry, we're not there yet. The pressure is constant, P, and then the volume is simply the difference between these two. It's going to be positive because it's going in this direction. Well, that didn't take long, did it? It wasn't too hard. Thank the Lord, if you're a Christian person. We're in the middle of coronavirus in New York here as I make this video. So stay tuned. This has been work done during volume changes.
Hi there! So, based on the video that I present to you, which is the work done during volume changes. So, work done during volume changes happens when a gas expands or compresses. Expansion means the gas does work on the surroundings. So, based on the example, katong cylinder, then ang kwan nito when a gas expand or compress, expansion means the gas does work, so nagtrabaho siya sa mga surroundings. It calls positive work. While compression means the surroundings do work on the gas, it called negative work. Compression means compress, kadugol-dugol. Means the surroundings do work on the gas, negative work. So, mga negative siya pag compress. Pag expansion, which is positive. So, now that we've learned about the first law of thermodynamics, which is the science for heat and work in thermodynamics and work during volume changes, let's see how will you understand this concept. So I'll give you the questions and answer the following question mentally or write down. Try to answer all questions before I give the solutions. This will help you check your understanding of heat, work, and volume changes in thermodynamics. Before we end, today we've learned about the first law of thermodynamics, which is the science for heat and work in thermodynamics and volume and work done during volume changes. So heat and work have signs to show energy direction, and volume changes cause work to be done either by the system or on it. These concepts help us understand everyday systems, from balloons to engines and refrigerators. Thank you for watching, and I hope this lesson helps you how energy flows all around us in real life. Once again, I'm Teacher Shin, and thank you for watching. I hope you have understand all my topic today. Goodbye, class.